Hello, this is Hong Tao from AI Assisted. This is the first part of what I'm hoping to be a series of videos on how to fine-tune or train a large language model. So today we're going to focus only on the data, so how to feed the data to the model for training and inference. And this is actually very simple. So let's get started. I've prepared a notebook. Also, I prepared some sample files to train on. There's a temp.py file and there's this a temp.rs file. This is so just two files simulate the training on a large quantity of code from the internet. So you can see those files are uploaded here. Very short. We're going to treat this whole file as text, as a whole string, and this Rust file. Yeah, so we're going to use these two as an example today. So let's first load these two into memory, and then they're in the form of one giant string. So this Python file is some of the most famous functions in programming, and then new line. I import functools, then new line, and then I start my definition. The first function is called foo, which is the most famous one. So you see the entire file has been read into memory as one string, and we're going to process that and feed that into the memory for training the language model for code prediction or code suggestion. Yeah, so let's suppose that our model expect an input of length 20, just as an example. So what would that look like? Let me run this. Yeah, so actually, no, let's just see the first 20 characters of the file. No, content, the first file, the first 20 characters of the first file. So it looks like this, sum of the most f. And then when the model sees a string, it actually contains a lot of training signals. So the model is gonna see the first character, which is hash, the hash sign, yeah, and then the model is gonna predict the next token, which is a space. So model is gonna see many training signals from the first character, which is nothing. The model is trying to predict the hash symbol, and from the hash symbol, the model is trying to predict the space symbol, and from hash plus space, the model is trying to predict a capital S, because that's so you can see the model is always trying to predict the next token, in this case characters, based on the previous tokens or characters in this case. And so this is just to illustrate the one training sample contain many training signals to train the model, and the model is always causal. Causal means the model only predict the next token based on the previous tokens or characters. And now I think the one of the big problem with this naive way of doing things is that each character contains very little information. So some of them M, the next character should be O, but it could be anything else. It doesn't contain enough information to make a confident prediction, because there are only so many characters, and each character can be combined in many different ways, and it just contains too little information. And one way to solve this problem is to introduce a tokenizer. A token is a string, basically. It's a sequence of characters. So sum can be a token, of can be a token, or even sum plus space of. This whole thing can be one token. So a token is essentially a sequence of characters which have some meaning to the model. And in this example, we're going to use some pre-trained tokenizers. Since we're doing code suggestion, we're going to use the tokenizer from Salesforce CodeGen model. So now I'm just going to load this tokenizer into memory. I think just give it a second. Oh, it's already done. Okay. So now let's look at what this tokenizer, how this tokenizer will tokenize our Python file. If I can remind you of what it looks like, the whole file. The whole file looks like this, a giant string. So let's see how tokenizer will treat this giant string. We run this. Yeah, so actually let me get it in one line so it's easier to look. We use a print. Yeah. So now we can compare this list with the original string. So you see the token hash is still by itself. The hash itself is a token, and then sum instead of SOME, it becomes one token. And this funny symbol, I think it just means space, or a continuation symbol in a tokenizer. Of it by itself is one symbol, and then there are some I imported func tools, and func tools has been divided into 3 tokens: fun, CT, and OOLS. So this is just the way this tokenizer treat the text. And the nice thing about a tokenizer is that each of these tokens have one ID, and we can get the IDs of tokens by using the encode function. Let me also get that in one line. Yep. So now the tokens have a one-to-one mapping to the numbers below. So this is ultimately what going to be fed into the model is a sequence of integers or a sequence of token IDs. And just as a sanity check, if we encode the entire file and then decode it, just to check we get the original file back. So run this. You see, yeah, that's the Python file we have. Yeah, so the tokenizer works. We can encode it and decode it and get exactly what we started. So after using the tokenizer, let's see what the training signal looks like inside the model. I'm just printing the first 20. Let's just suppose the model expects input length 20. So when there's nothing, the model is trying to predict token number 2. When there's token number 2, the model is trying to predict 2773, and so on and so forth. One thing that is really neat is that we only need to supply one input sequence like this. We only need to supply this one sequence to the model, and inside the model, it will somehow break it down into all these 20 training examples. So we don't need to worry about breaking down the training examples here in the data loaders. We just need to supply this one sequence. And now here is just I'm tokenizing because we're training on 2 files in this example, 2 files, Python file and Rust file. So here I'm just gonna tokenize both files at the same time, and then they're gonna come up as as 2 lists. So just for readability, I only tokenize the first 100 characters. So you can see it's a list of lists. The first list corresponds to the first file, and then yeah, here's the start of the second list, and that corresponds to the second file. And now I'm going to talk about how can we construct a batch from this, a list of integers, or a list of tokenized content. How can we construct a batch from this? So I have this picture, which is that illustrates the idea very clearly. So let's suppose we have 3 samples or 3 files tokenized. So each of this yellow block is a number, like 3 or 198, and they have different lengths. And what we do is we concatenate them. So this is the first file. You can see this block is the first file, and then these 4 yellow blocks are the second file, and then the third file. And then very importantly is that in our concatenation between separate files, we insert a EOS token. EOS stands for end of sequence. So when the model sees this token, it will stop generating. Or in the case of inference, or in the case of training, it will ignore the training signal after this token. So we concatenate all 3 files, and in between them we insert this end of sequence token, EOS token. And yeah, I have a function to do just that. It's called concat. So let's see what it looks like after we concat our 2 files. So this all token IDs is this one. We just look at it here, and then we're gonna separate them by the EOS token. Oh yeah, I haven't run this. Yep, you see they are almost exactly the same. 2773, 286, 286, except the only difference is that this is a list of lists, and this is just one list of integers. And if you scroll to the end of the first sequence, which is here, let me find that. It's 7203. Oh, I couldn't find it. Yeah, okay. 7203 21943. Yeah, so that's the end of the first sequence. See here? That's the same. And then the start of the next sequence is here. See? So in between them we have an end of sequence token, and the token ID happen to be this number. So that represents the EOS token. So now using this function, we've concatenated all the files, tokenized content, all the tokenized contents of all the files into one giant sequence of integers. And now we're going to randomly draw our batch from this one long list. And we have a small function to do that. So in this case, in this example, I'm gonna assume the model expect that the input length to be 10. So just so we can see things clearly, and then I'm drawing 6 samples, meaning batch size is 6. So basically, what I'm doing is randomly select a index or a token, for example 286, and then get the 10 tokens from this 286. For example, maybe that's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, here. So I get this. That is one sample in my batch, and then I'm gonna draw another random token here, and then 10 tokens afterwards as a second item in the batch. So very simple. And so if I run that, I draw a batch. Yeah, it's gonna end up with a tensor with shape 6 by 10, so 6 independent examples, and each example has 10 sequence lengths. And inside the model, each example here is going to turn into many different training signals. So in this case, 9 training signals. So in total, with this one batch, I have 6 times 9 number of training signals, all compact in this one batch. So if I run it again, every time it's going to be different because it's random process. Yeah, so that's pretty much it. This is very simple because the breakdown of one training example into many training signals has been taken care of for us inside the model. So in the data loaders, we don't need to worry about that. And in a real world application, this will typically be 2086, and batch size would typically be a large number, like file 12. So that's more like a realistic scenario. And realistically, this list of integers concatenated tokens from different files is going to be also very long, like 30,000, 40,000 something. Yeah, so this is just a toy walkthrough of what the data loader is doing and how we are going to feed the model for training large language model. So I'm hoping in the next series I'll walk through the training loop, so see the training in action, and then I'm gonna dive deep into the model itself to explain where this got broken up into many smaller training signals, and also the causal relationships. How can we make sure that this token is only predicted based on what's before it? So I'll see you next time. Bye bye.